In this video of Graph Theory Part 5, we will discuss about planar graph. We will see a few examples of it, region, and we will verify Euler's formula. So let us begin with planar graph. A graph that can be drawn in a plane so that its edges do not cross is said to be planar graph. So here we have a graph having edges A, B, C, D, E. Here we don't have any crossover. So this is an example of planar graph. It is drawn in a plane and its edges are not crossing. So it is a planar graph. Now here in the second diagram, part A, we can see a complete graph, K4 graph. It can be redrawn so that no edges cross. So this is also an example of planar graph. Next is non-planar graph. A graph that cannot be drawn on plane without a crossover between its edges is called non-planar graph. So we have a K5 graph which is not planar. Here the edges cross each other at E. So this is an example of non-planar graph. Next we will see some examples of non-planar graph, that is Kuratowski's 2 graph. This is example of non-planar graph. So first graph of Kuratowski's. Here we can see that every vertex, this is a complete graph of 5 vertices and it is non-planar. So here every vertex is joined to other vertex by means of edges. V1, V2, V2 to V3, V3 to V4, V4 to V5 and again from V5 to V1. Circuit from V1 to V2, V2 to V3, V3 to V4, V4 to V5, V5 to V1. It forms a pentagon. An edge between V1 and V4 cannot be placed inside or outside the pentagon without a crossover. So here let us see the pentagon. After drawing this pentagon, it is V1 and V3 is joined. So this is also a planar graph, but here V2 and V5 are joined with an edge. V2 and V4 is again joined with an edge. In the next one, V5 and V3 are also joined. Now the only two vertices which are left is V1 and V4. So an edge between V1 and V4, the moment we will draw this edge, we will get a crossover. And thus this graph is a non-planar graph. Because in a non-planar graph, the edges do not cross. So this is Kuratowski's first graph of 5 vertices and it is non-planar. Second one is Kuratowski's second graph. Here it is K33 graph. Here we can see that two edges are crossing each other. So this K33 and K6 graph are non-planar. So what properties are common to both the graphs of Kuratowski's? That both graphs are regular graph. Both graphs are regular graph, both are non-planar. All the vertices are of equal degree. And one more thing we can observe is removal of 1 degree or a vertex make each a planar graph. the moment we'll remove one edge here, it is a planar graph. So these are the several properties common to two graph of Kuratowski's graph, and this one was the example of non-planar graph. Next, we have a term region. Now what is region? An area of the plane that is bounded by edges of the planar graph and is not further subdivided into sub-areas is called a region of the planar graph. Now regions are of two types, finite and infinite region. A region is said to be finite if its area is finite, and it is said to be infinite if its area is infinite. If we have a planar graph, it has exactly one infinite region. So let us consider one example. Consider a graph G. Here we have a graph G having 10 vertices. So this is a graph, and here we will show the infinite region and finite region of this graph. So the outermost part of this graph, it is shown by the shaded part. This is the infinite region of this particular graph. And the finite regions are how much? This is 1, 3, 4. 1, 3, 4. This is the first part, 3, 4, 8. This is the second part, the smaller one, 5, 6, 7, and the fourth one will be 3, 9, 8. So here the finite regions are 1, 2, 3 and 4. So total number of regions, finite and infinite, of this graph is 1, 2, 3, 4 and 5. So here we have seen that a planar graph has exactly one infinite region. Next, we will go through Euler's formula and will verify the Euler's formula. So what is Euler's formula? In a connected planar graph G with V vertices and E edges and R regions, we have V minus E plus R is equal to 2. V is the vertices, E number of edges, and R the number of regions. So V minus E plus R is equal to 2. This is known as Euler's formula. So let us verify this formula in graph. So here I have taken two graphs. For the first one, let us see the first graph. Here we have 5 vertices, 1, 2, 3, 4, 5. So here what we have to find out in these two graphs? Number of vertices, number of edges and number of regions. So for the first graph here, we have number of vertices is 5. 1, 2, 3, 4, 5. Number of edges is 1, 2, 3, 4, 5, 6, 7, 8. So number of edges is 8. Now we have to find out the regions. Regions are finite region plus infinite region. So here we have 1, 2, 3, 4 and 5. So region is 5. Let us put the values in the Euler's formula. 5 minus 8 plus 5, that is 10 minus 8, which is equal to 2. So Euler's formula is verified for this graph. Let us see the second graph. Here the number of vertices is 3. Number of edges is 1, 2, 3. This one is 4, 5 and then 6. Number of regions are 5. 1, 2, 3, 4 and 5. So let us put the values in the Euler's formula. Again 3 minus 6 plus 5, that is 8 minus 6, which is 2. So for both the graphs, the Euler formula is verified. Now we have a theorem. Let G be a connected planar graph with V vertices, E edges, and where the number of vertices is greater than or equal to 3. Then E is less than equal to thrice of the number of vertices minus 6. So here what is given? Here given G is a connected planar graph where number of vertices are V, number of edges are E, and one condition given to the vertices that it is greater than equal to 3. Then we have to prove this. So let us start the proof. Let R be the number of regions in a planar representation of the graph G. So R is what? The number of regions. The sum of degree of regions is equal to twice E. But each region has degree greater than or equal to 3. It is given. Hence, twice of E is greater than equal to 3R. So what we can write? R is less than equal to twice E by 3. Now we'll put the values in Euler formula. Euler formula is V minus E plus R is equal to 2. V, in place of V, it will be V. E, it will be E. But in place of R, we'll write 2E by 3 from 1. So here it will be V2 is less than equal to V minus E by 3. On solving this, we'll get 6 less than equal to 3V minus E. So this we have got a formula. Let us verify it, or let us see with one example. Show that the graph of K5 is non-planar by using this formula. So here we have a graph K5 which is non-planar. This is a complete graph with 5 vertices, 1, 2, 3, 4 and 5. And number of edges here is 10. Suppose the graph is a planar graph. We'll consider that this graph is a planar graph. Then if it is a planar graph, E is less than equal to 3V minus 6. Now we'll put the values. We got a contradiction that 10 is less than or equal to 9, which is false. Hence, this K5 graph is a non-planar graph. Thus, we have seen that what is a planar graph? It's example of non-planar graph, region, and we have verified Euler's formula. Thank you.